Okay, so let's consider question 3. Question 3 also conveys 3 questions. The A part says explain atomic packing factor and prove that the atomic packing factor for FCC structure is 0.74. Alright, so I've done this particular part on my recent video of material science. So I'm just going to drop the link in the description of this video below so you can just watch it up for yourself. There's no need to redo this particular part again. But then let's move to the B part. The B part says draw the 110 plane and calculate the atom per squared centimeter of the plane. If the lattice parameter is 4.05 Armstrong units and the plane belongs to the FCC. Again, it says calculate the interplanar spacing between the 110 plane above. Okay, so we're asked to draw the plane of given Miller Index. So we're given the Miller Index as 110 and we are to draw this plane. So like I said, to draw a plane in the Miller Index, this plane actually, or this Miller Index signifies H, K, L. So which means H equals 1, K equals 1 and L equals 0. So to draw the given plane, we need to find the intercept of the Miller Index. So for the x-intercept, we consider x x to be equal to 1 all over h, which is equal to h here is equal to 1, so it becomes 1 all over 1, and therefore our x plane becomes 1. Our y-intercept, we consider y to be equal to 1 all over k, and k here is also what 1. You have 1 all over 1, which is also equal to 1. And for the z-intercept, you have z to be equal to 1 all over l, and this is equal to L here is 0, so you have 1 all over 0, which gives us infinity. Okay, so which means our plane now become the intercept of the Miller Index. The plane is x, y, and z, and this is equivalent to x gave us 1, y gave us 1, and z gave us infinity. So we have to draw this x, y, and z to infinity, x to be 1, y to be 1, and z to infinity. So let's start by drawing our simple cubic structure. So we'll put down our simple cubic structure. We'll have this. Okay. Alright, and this is my z direction. You can choose any direction at all. This is my positive z direction. And this is my positive x direction. And this is my positive y direction. Now, this is actually a simple unit cell, which means each distance apart is 1 meter from the origin. So from here to this point is 1, from 0 to y here is 1, from 0 to x here is 1. So we can always find half to be in between. Now we want to the plane cuts x at 1, so x here is 1, from the origin is my x plane, and this is 1. It cuts y at 1, so from the origin this is y is 1, from the origin this is y is 1, and it cuts z at infinity. This simply means that this x and y plane, okay, if I join this point now, this is 1 for x, this is 1 for y. So joining these 2 points together, if I'm joining these 2 points together, I'm going to have, okay, this is my x and this is my y. Alright, so I have this. So this simply means that this plane, x and y plane, is parallel. For it to be infinity on the z plane, it means it's parallel to the z plane. That means it can never cut across the z plane. So what it simply means is reproduce what you have here on the z plane. So simply connecting here to this point, because this is your x as well and this is your y as well. So reproduce what you have here on this plane. But the other way to explain this is, I can, since it is parallel to the z plane, then you can call the z plane your origin. The infinity point becomes now your new origin. Now remember, it cuts x at 1 from origin. This is my x is 1 maximum here, and then it cuts y at 1 from the origin. This is y is also 1 here. So you still join them together, it still gives you the same thing. Okay, you join these 2 points together and you have what you have on this other plane. So it means producing what you have here on this side, on the plane that is parallel. So this means now that the x and the y plane, okay, this plane now is parallel to the z plane. It can never cut the z plane. So this becomes the 1 1 infinity plane. So you can, okay, can choose to do this. All right, just to isolate the plane. So this is now the 1 1 infinity plane, 1 1 infinity plane. Okay. Now the next question, still on the B part, says calculate the atom per squared centimeter of the plane if the lattice parameter is 4.05 Armstrong units and the plane belongs to the FCC. Okay, so we are to calculate atom per square meters and we are given lattice parameter. So we are given the lattice parameter or lattice constant A to be equal to 4.05 Armstrong units. So always convert your A to centimeter. That becomes 4.05 multiplied by 10 to the power of minus 8 in centimeter. Now we are asked to find the atom per square unit. Okay, atom per squared centimeter. We're asked to find the atom per square centimeter given this lattice parameter. And then the next question says, what is the interplanar spacing between the 110 plane above? So in order to find the atom per square meter, the first thing to do is to find the interplanar spacing already, but it was still part of the question. Okay, we have to find the atoms per squared centimeter. Oh, all right, unknown. But in order to do this, the number of atoms per square centimeter n is actually given as 1 or 0.5 divided by d to the power of 2. All right, so that becomes atom per square centimeter. So we need to find d, where d is the interplanar spacing or distance, equals interplanar distance or interplanar spacing, as the case may be. So we need to find first the interplanar spacing d. For the given plane 110 is given as the Armstrong units all over the square root of the sum of the squares of the individual Miller Indices. So you have h squared plus k squared plus l squared. So this is equal to A stands for the what? Lattice parameter. Okay, this was supposed to be small a. Alright, and lattice parameter was given as 4.05 by 10 to the power of minus 8 in centimeter all over the square root of, remember from our Miller Indices, we obtained that h is equal to 1, k is equal to 1, and l equals 0. So we'll plug it back into this equation now. You have h squared becomes 1 squared plus k squared also 1 squared plus l squared becomes 0 squared. So the interplanar spacing for 110 plane is now equal to 4.05 by 10 to the power of minus 8 all over. This is square root of 1 squared is 1 plus 1 squared is 1 plus 0. So you have 4.05 by 10 to the power of minus 8 divided by square root of 1 plus 1 plus 0 is 2. So let's do this all at once. So this simply implies that the interplanar spacing for the 110 plane is now equal to, okay, let's do that at once. So I'm going to be dividing all through just to save time. 4.05 exponential minus 8 divided by root 2. So that gives me 2.87 by 10 to the power of minus 8. So interplanar spacing is 2.87 by 10 to the power of minus 8 in centimeter approximately. So if you have this to be the interplanar spacing, okay, if you have it to be the interplanar spacing, now we need to find the atom per square centimeter. Like I said, you simply use this as your formula. N is equal to 0.5 divided by d squared. Okay, now we have n number of atoms equals 0.5 over d squared. So this is equal to 0.5. D there give us 2.87. So you have 2.87 by 10 to the power of minus 8 all squared. Alright, so I'm going to be pointing this all together as well just to save time. So I have 2.87 exponential minus 8 all squared. Okay, 0.5 divided by answer. So I have 6.07 by 10 to the power of minus 14. Hence, this implies n is equal to 6.07 by 10 to the power of minus 14 atoms per centimeter squared. Alright, I have this to be the final answer to that question. And then the last part of question 3, the C part says, iron has cubic structure and its atomic weight is 55.84 with density of 7,900 kilograms per meter cube and a lattice constant of 2.88 Armstrong units. Determine the type of cubic structure. So let's put down our parameters. We are given that iron has a cubic structure and its atomic weight is 55.84. So atomic mass, okay, atomic mass, capital M was given as 55.84, of course, in grams, okay, with density of 7,900 kilogram per meter cube. So we're given density D to be equal to 7,900 kilogram per meter cube. So do well to convert this to gram per centimeter cube because density is usually measured. Like I said, in this part of the world, in Rivers State University, you always convert to especially your lattice parameter, your density must be in gram per centimeter cube. Okay, so you divide through by 1000 to convert this to gram per centimeter cube. If you divide it by 1000, you're going to have 7.9 grams per centimeter cube. That becomes the value of your density. Okay, and lattice constant of 2.88 Armstrong units. So you are given lattice constant. A was given as 2.88 Armstrong units, which equals 2.88 by 10 to the power of minus 8. Once again, convert to centimeter. You have this. Now they're asking you what type of cubic structure is this. So it's very simple. You employ the equation for density. Recall that density D is actually number of atoms times molecular weight or atomic weight all over Avogadro's number, okay, multiplied by volume of the atom. So which means if we look through the given parameters, we're given density, we're given atomic weight, we know our Avogadro's number is a constant value, we are given lattice parameter so we can find the volume. So the only property we are not given here is the number of atoms. So all we need to do is to make number of atoms subject of the formula and then see how many number of atoms we can find, then compare that with the number of atoms in each of the cubic structures we are aware of. So this is equal. This now implies to make n subject, you cross multiply, density multiplies everything under here. It becomes density times Avogadro's number, VAV, times volume, okay, and that is equal to, you have here n times m. So we simply make n subject. This implies that the number of atoms becomes density times Avogadro's number times volume all over atomic weight. So let's find the volume now, where V, which is the volume, is now equal to A to the power of 3. So V is equal to, A was given as 2.88 by 10 to the power of minus 8 all to the power of 3. This simply implies that our volume V is now equal to 2.88 exponential minus 8 to the power of 3. So you have 2.39 by 10 to the power of minus 23. That gives us approximately 2.39 by 10 to the power of minus 23 in centimeter cube. So we have the volume now in centimeter cube. Let's plug into this equation for n. Therefore, n is equal to, density was given now, we've converted density to 7.9 gram per centimeter cube. Okay, so you have 7.9 multiplied by Avogadro's number remains 6.02 by 10 to the power of 23 multiplied by the volume now is 2.37, sorry, 2.39 by 10 to the power of minus 23 all over the atomic weight, which is 55.84. Alright, so having this now, number of atoms n becomes, let's apply the numerator all through. I have 7.9 multiplied by 6.02 exponential 23 multiplied by 3 points, sorry, multiplied by 2.39 exponential 23, sorry, exponential minus 23. So the numerator gives me 113.66 approximately divides by 55.84. So this implies that n is equal to, divide that answer by 55.84. We have n to be 2.0, okay, approximately 2.0. Now, the number of atoms is given as 2.0, and we know that the body center cubic structure, the BCC structure, has 2 atoms. Okay, it has 2 atoms. Hence, iron is a BCC structure. Alright, so iron is actually a BCC structure since we obtain the number of atoms to be equal to 2. Alright, so that's it for that particular question.